All right, let's get started. Either the cold has wiped out half our class or the first homework took a big toll. Not sure which. Hopefully it was the cold, not the homework, but we'll see on Thursday or maybe. We usually do lose a lot of people after that first homework. Turns out people think that's hard. So hopefully you guys got the first homework in. Remember, if you didn't, you can still submit it. You can submit late. There's a 5% penalty a day, up to 30%, I think we said, or 25, something like that. So you can submit late, and if you totally screw up a homework, you can actually resubmit after it's been submitted. If you submit a homework that did better, you get let's say you got 50% on your homework. You could try again, and you'll get a 25% penalty for being late, or 30%, depending on what it says on the website. I can't remember. But you could still do better than if you totally screw up your homework. You get one resubmission after the fact. And if you do that, make sure you ask for a regrade through Gradescope. Otherwise, we might miss the fact that you resubmitted after the fact. But you only get one of those. Don't just keep submitting homeworks over and over. Generally, you want to get them right in the first place. All right. Was there a question there? Okay. All right. The next homework is out. Hopefully, you guys are already working on it. But it is the kind of stuff we're talking about today, so probably not many of you are. We'll be finishing up this stuff today, and then you should be ready for the next homework. The third homework's actually out too, but that's stuff that we're not going to cover for a couple days. Is there any questions before we get started about the homework, about anything that happened there? Okay, cool. All right, so we've been talking about SVMs. I always say SVN instead. SVMs are support vector machines. Support vector machines are a type of classifier that uses a linear boundary to classify things. So just as a recap here, we got a support vector machine. It's linear. We're going to look at that in a second to see what that means. There's two parameters that we have to worry about with a support vector machine. There's the A parameter, which is a vector, and then the B parameter. And you end up forming this expression, which is A transpose X, where X is sort of the input that you want to predict, or the input vector. A transpose X plus B, and then the class you assign is going to be either 1 or -1, depending on whether you are positive or negative on the sign of that AX plus B. So we just look at the sign. If it's positive, a positive, we call that a positive. If it's negative, we call it a negative. SVMs are not very amenable to doing more than two classes. The book will talk about a couple ways that you can do that. They're not the best if you have to do multiple, 3 or more classes. So we started, or we were talking about we were talking a lot about the feature space and how this, how you build this AX plus B and how to visualize it. And a couple people had asked afterwards, and it was clear that I wasn't doing a very good job at sort of giving the intuition about how these sort of the feature space and the plane goes together that divides it. So I'll try again. This stuff is hard to talk about because we're always talking at a dimension higher than what I can draw. So here, if we have our feature space, let's say we have sort of some x1, x2 features. And they're in a plane, so it's two-dimensional. And we have a bunch of points. These little dots are on the plane itself. So I labeled those examples 1 through 6. What we're going to do is we're going to learn this second plane, AX plus B. It's going to be in one higher dimension. So it's essentially going to add a dimension to this. And so you can think about it this line right here is where this plane that I have drawn and ax plus b cross. So with a value of 0. So basically this is the intersection of two planes, so they're kind of crossing each other. So ax plus b is actually sticking out of the sort of the paper. And what I've tried to draw here is like these little x's are the ax plus b of the different, associated with the different elements. So you can see they're kind of up out of that plane. And this plane would be sort of tilted, you know, it would pass through all these x's, go through this little dotted brown line, and then pass through this set of small little x's to define things. Question? The x's, yes. So in this case, the x here, this x should be ax, a vector of x1 and x2 in this particular diagram. So when we talk about, anytime we talk about this, this ax plus b, it's sort of sticking out of the plane. It's a plane that, you know, for every point in here, it's going to have a value that's sort of outside of this plane, but it intersects and it forms a new plane. So is there questions on that? Are people kind of getting an idea of how to visualize that? It's a hard thing to visualize on this because it's, you know, it's slicing through the, you know, from out in the air here down into the paper. But a lot of the stuff that I was drawing the other day, I kind of would draw away from the line to indicate the ax plus b was really high. And that was probably, I know was confusing a couple people that came and asked afterwards. So I'll see if you guys are done scribbling this. See a couple people still writing. So we're going to have to find the we're going to have to find some A and B that does the classification. Remember, one side of this line, which I labeled right here, it's going to be greater than 0. So everything over on this side of that little brown line is going to be labeled as positive. And everything over here is going to be labeled as negative. And if one of these points that happen, I didn't label any of these points as positive or negatives as labeled, but if they happen to be on the wrong side of that line, that's when a misclassification occurs. And that's when we're going to pay some cost for that misclassification. So we're going to try to find, hopefully you guys mostly have that. We're going to try to find some A and B that minimize a cost. A lot of the mechanisms we have for learning are going to use this similar kind of system of you define a cost of, say, the cost, which you can think of as sort of a penalty for making mistakes. This is a specific one for SVMs. Other classifiers and other regression, when we get to that, will use different ones. But they're always going to be sort of similar. They're going to have, you know, they're going to have some parameters like A and B. They'll have the input vector. They'll have the label. And given all that, there'll be some cost for choosing any given A and B. So here we can look at the cost for the SVM. The U, we're just gonna stick the A vector and the B into the same vector. That's just the way it's usually written to make it concise down here. So your cost is going to be a function of U. To do stochastic gradient descent, we talked about the gradient descent. Basically, gradient descent is you sort of just update this sort of iterative update of the parameters that you're trying to learn over time by taking the gradient with respect to the parameters, evaluate them at the current parameter setting. So you start with some parameter setting, U0. You look at the gradient, and then you take a move. You move a little bit in the opposite direction of that gradient. So you take the current estimate, you move by some eta times the gradient evaluated at the current estimate, and that becomes a new estimate. that estimating, that iterative process of just applying the gradient over and over is called gradient descent. Now, just at the end of the class, I can't remember quite where we were, but we started talking about if you have a really big data set, gradient descent is really inefficient. Because if you have a billion data points, calculating a single step of the gradient would be, O of a billion. You'd have to go through all of these data points. And often that isn't necessary. Often you can get a really good estimate of the gradient just by taking a small sample of data points. In expectation, that sample will be equal to the real true gradient. So as long as you take lots and lots of samples, over time they will push you in the right direction. Now they'll be noisy, they'll sometimes go in the wrong direction, they'll sometimes be the wrong size. But stochastic gradient descent relies on taking a random batch of samples that are much smaller than your full batch. So we update the gradient descent just by having a first step that selects a random batch of size NB. And as I said, that size can be as small as 1, and it can be much, much bigger. And we'll talk about how to sort of size that in a second. Other than that change, its stochastic gradient descent is the same as gradient descent. You calculate the gradient only on the batch, which means that instead of averaging over, some n examples, you're going to average over some NB examples, some much smaller number of examples, to get your cost function. But the math that goes into calculating the gradient is exactly the same. There's nothing different there. It's just a much smaller batch you're working on. All right, so let's, any questions so far on that? All right, sounds good. So let's actually look at what the gradient is for this particular expression. So, so we want the gradient with respect to u of the max of 0 and 1 minus yi times A transpose x plus b plus lambda over 2 A transpose A. So again, the U has two components, the A component and the B component. So you'll really have to do two partial derivatives here. But this is going to be equal to the max of, let me see where I got this, of 0, and the derivative of this second part, again, it will have two parts, one based on the A and one based on the B. So that becomes, for the A part of it, it just becomes negative yi xi. And for the B part of the gradient, we have just this. And then, again, there's going to be two parts for the derivative of this. For the B, it's equal to 0. And for the A, it's going to be, I'll drop the lambda there. It's going to be just the A vector itself. So that's that is the gradient that we're going to have to apply. So each step, we're going to evaluate this function and apply that step to move your parameters closer and closer to where they're supposed to be. Okay, so there's a couple things we glossed over a little bit. First thing you have to do is you have to find, we have a lambda there that we have to find. That lambda, we talked about it a couple days ago, but it's just a hyperparameter. Hyperparameters basically mean that you have a choice that sort of is such high level that it falls outside of the normal learning procedure that we usually use. So it's not going to be the gradient descent that determines the lambda. You sort of have to choose lambda first. And the way we always choose hyperparameters is through some sort of some through a validation set. So we'll set aside a validation set of some amount, and we'll train multiple models with different lambda values. And for each of those different lambda values, it'll create a model. We'll take that model and we'll test it against the validation set. We might, if we need more statistical power, if we don't have enough data, do cross-validation. So we might train 10 models for each of the different lambda settings with 10 different distinct validation sets, and then average over those validation scores. And we do that to select our lambda. So lambda's pretty straightforward to select. We didn't talk about yet much about, where did this go? We didn't talk about this eta yet. This is called the step size, or often the learning rate, especially if you're doing neural network stuff. It's often called learning rate. But step size, it's basically how much of that derivative you're going to apply each time. How much of the gradient are you going to apply as an update? And there's a couple rules that we can use to sort of select this eta. So just from intuition-wise, there's kind of two properties we want. One is that we assume when we first start, we're starting at this U0, and this is completely uninformed. This is just some point out there that we chose randomly. Because we just chose that randomly, we don't know how good it is. We could probably assume we're pretty far away from a good solution there. And so early on, we probably want our step size to be fairly high. And then later, as we get closer and closer, we probably want to reduce our step size so that as we get closer, we don't sort of overshoot or go running past the minimum. So we actually want our step size, as our prediction improves more and more, we want our step size to go down. So generally, that's going to be what we want with our step size, is something that starts fairly big, decreases over time. From a theory perspective, we can actually have a guarantee. Any sequence where the limit as our iterations go to infinity and eta goes to zero. That's property 1. And 2, where as our iterations go to infinity, the sum of all of our different learning rates over time, get the right parenthesis, goes to infinity. If we have those two properties, we're actually guaranteed to converge asymptotically. So basically what it says is that you have to take increasingly smaller and smaller steps, but you always have to be able to have an infinite amount of distance you can cover. So you can never go down to a step size of 0, but you want to keep getting them smaller and smaller. So basically what this means is that over time, we're going to take we're going to change the step size that we take each iteration. So if we go back to this stochastic gradient descent guy, what we actually want to do is add a k here. And this k is going to be some indicator of how long have we been training, how long have we been applying this. And this is often called, it's often called the epoch, which technically means how many times have we gone through the data, or the book refers to it as a season, which is just sort of a big chunk of data that we've processed. Possibly not all of it, but a big chunk of data that we processed. And the idea is that as you process more like let's say as you process every 1,000 examples, you would increase k. And each time you increase k, you're going to decrease your learning rate. So the learning rate we'll end up using is going to be something, let's say it's going to be some n over k plus n. And these guys we're going to choose so that the learning rate kind of is in the right range that we want it to be, but it still goes down at kind of the right pace we want it to be. And they're actually kind of tough to choose, but what we can see here is if m and n are really big, then it's going to take a really long time to reduce the learning rate, because that k won't have a very big effect. But if we use m and n of, say, maybe 1 and 2, if m was equal to 1 and n was equal to 2, we'd start at season 0, we'd start at a learning rate of 0.5, and then as soon as we hit season 1, we'd be at a learning rate of 1/3, and then 1/4, and 1/5. So it would go down fairly quickly. The M&Ms don't have to be integers; they can be something smaller. But kind of the idea is that you want some sequence that's going to be adjusted by the number of seasons that you've taken, the number of big batches that you've processed of the data. This could even be just the number of batches that you've processed. You could just count those, but you'll probably need your M&N to be pretty big then. So if you're counting, say, the number of batches, you're going to do thousands and thousands and thousands of batches over time. And so M&N would have to be pretty big in order to counteract how quickly K will grow. So there's the learning rate. I want to talk about this really quickly, and then I'm going to show you a demo. But the learning rate is going to have, selecting the learning rate is hard because you don't really know how good your accuracy is going to be in the end. You don't really know how fast you'd expect it to converge to that accuracy. There's a lot of unknowns when it comes to a new problem. You don't really know what a good learning rate is going to be. But when you're tuning your learning rate, you're going to try a bunch of different ones. And what you want while you're learning, what we're going to do is we're going to graph each season. Again, we talk about a season of being, let's say, if you had 1 million data points, maybe a season is every 10,000 data points. We would call that a season. And then each season, what you're going to do is you're going to set aside a little random validation set. And you're going to judge the accuracy on that random validation set for that season. So what it might look like if we looked at our data is we might have something like this, where this is all of our data. Well, first of all, we need to set aside some test data. That stuff is going to be used at the very end, so we're not going to touch that. Then we have some hyperparameter, which we know about. So we got to have a lambda validation set. So that's the lambda validation set. And so this is basically the training set that you would use during training. And what we need, in order to do kind of a good evaluation of is our learning rate set correctly, each season, every, say, 10,000 data points, we're going to take some random, we're going to resplit this training data. So we're going to take some random selection. We're going to say that this is the season validation set, and the rest of it is going to be the training validation set. So for that season, we're going to train on this stuff. We're going to evaluate on this stuff, and then we're just going to keep a graph of our accuracy over time. And each season, we're going to reset what this validation set is. So we're going to reshuffle this stuff every season. So basically, we want to make sure that we're training on all our data. This validation set isn't as important, just a second, isn't as important to keep sort of pristine and clean. We want to make use of as much data as we can, but we still do want to have some sort of indicator of how good that epoch was. So it's not quite as clean as setting aside a completely separate validation set, because we're constantly mixing it back in, but we're only mixing it back in every, say, 10,000 data points. So hopefully by the end of that season, we only evaluate at the very end of the season. So we train 10,000 data for 10,000 data points. We evaluate on that season's validation set. We reset things. We train for another 10,000. We evaluate, and we can sort of do this iterative thing. So even though this season's validation set is going to keep getting remixed into the training data, that's okay. It's not great. We'd rather set it aside. If you have enough data, it might make a sense to set it aside. But most of the time, we want to throw it back in. But in any case, let me take that question before I forget. Oh, definitely. If I do that again, wave a lot more. Yeah, sometimes I forget to move it. So we're going to come up with doing this process. We're going to come up with some graphs. And the graph is going to look like this. First, you're going to have, this is going to be the season, which we're going to call K. And it's going to go, some number of seasons. And then you're going to plot either the accuracy or the error on this side. And this is the validation accuracy from that small hold-aside set that we've been using. And to choose your learning rate, both initially and over time, like how fast it's going to go down, you're going to want to look at this graph for different learning rates. So basically, you're going to try a bunch of different learning rates to see how they react. And there's a couple ways that they can react. So usually you'll start, if you're talking about accuracy, we'll start down here somewhere. If you have a good learning rate, hopefully your accuracy is going to go up, but it's going to have some noise. But it's going to keep going up until you asymptotically get somewhere there. So it'll look something like that. Now, why does it have noise? It has noise because we're doing stochastic gradient descent. We're taking samples, and so we might occasionally move away from the best solution. We might not always be heading towards the minimum because we've taken a sample. But assuming those samples asymptotically move in the, asymptotically those samples will point in the right direction, we should go upwards like this. Now, other things that can happen is you might get something that looks like this. So this one is good. You might get something that looks kind of like this. There might be some variation in it. This one is too low of your eta. Basically, you don't have your learning rate high enough. You're not really moving very far each time. Now, asymptotically, that might make it to the minimum eventually, but it might take you forever. If your learning rate's too low, it might take you a long, long time to get there. But the one thing you really don't want is something that looks like this. This one, in hindsight, I should have done this in different colors. This one is too high. And basically what you're doing is you're probably jumping past the minimum. So if you think about you're sort of trying to get down to the bottom of this parabola. In this case, it's a parabola because it's a convex function. So we might be moving down, but if our learning rate's too high, we might skip out right past the minimum and go back up the other side. And we might do that repeatedly and go back and forth and back and forth. And we might actually diverge where we get farther and farther away from the minimum each time. So if you see a lot of variance and you see a lot of jumps, and it's not really moving upwards, your learning rate's probably too high. In general, even though it's a little bit non-intuitive, if you have trouble learning, you want to reduce your learning rate. Learning rate being too high is the biggest reason for stochastic gradient descent failing. And everybody's like, well, I want it to learn fast. And the fact is that if your learning rate is too high, you will skip past the minimum and you'll lose a lot of your progress. Okay, so any questions on that? This is the season validation accuracy right here. This guy right here is, we're making a graph that is, this is the season, and this is the accuracy on this validation set that gets dropped and recreated each time. And that's just because we want, while we're learning, and you don't probably do it, if you train 10 different values of lambda, cross-validated again across, maybe 10 folds, you'd be training 100 models. You probably don't want this particular graph for every 100 models because then you'd have 100 graphs to look at. So it's probably for each value of lambda, we want to choose one of the folds maybe and look at this sort of learning rate. The learning rate is something that generally you have to tune once for all of the different values of lambda. So sometimes, there is a kind of an independence of whether, So here's the thing: is normally you would be training maybe 10 different lambda values using this training set. But you do need to also choose the learning rate. And so the question is: do you choose the learning rate inside of the lambda loop, or do you choose the lambda inside the learning rate loop? The learning rate generally, once you find something that's in the sweet spot, you won't need to adjust it for different values of lambda. So really what you want to do is the first time you bring up your learner, you'll want to do kind of this graph to kind of get an idea of what your learning rate should be. And then once you have an idea, you'll probably use that same learning rate for all of the different lambda models that you try to create. That's pretty common. Now there is an interaction, so sometimes you have to find a lambda that's sort of in the area of being pretty good, and then find a learning rate that works for that, and then usually that learning rate will work for all the other lambdas. But there is kind of an interaction there. This is a little bit of a chicken and the egg problem. You can't test whether a lambda is good until you have a good learning rate. You can't really determine the learning rate if your lambda is completely out of the blue in a different spot. So you got to play around a little bit on some of this stuff. Okay, questions? That always depends on how much data you have. If you have enough data, you don't need to do cross-validation. You can just do a bigger set. There's a limit to that. So it depends. Okay, so there's a lot of different reasons you might do cross-validation. One, if you don't have enough data, you might do cross-validation to get more statistical power. Because you can sort of reuse the data multiple times. You train 10 models using different test sets each time. You average over, and you get a little more statistical power that way. The other thing is, if your models themselves have some variance in how good they are, for example, we won't talk about them yet, but neural networks have a random component of where you start, basically. And so often, just by luck, sometimes a neural net will learn really well, sometimes it won't learn quite as well. And if your model has a lot of variance in it, sort of how good it's going to be at the end, then you also might want to do cross-validation. Because you might want to say, oh, sometimes this model comes out bad, sometimes it comes out good, let's see what it does over average. But a lot of it has to do with how much variance is there in the model. Most models we're talking about don't have a lot of variance. In fact, decision trees don't have too much, they have some. Naive Bayes has none. It's a deterministic. We just calculate the numbers. Nearest neighbor has none. You'll get the same model for the same data each time. So it depends a lot on that. Generally, if you have enough data, though, you don't do a lot of cross-validation. Cross-validation is very expensive. It takes, and as our models get more and more complex, which they will as we go into more complex modeling techniques, the amount of time you can take to do 10 models instead of one, all of a sudden it's like, well, am I going to take a week to do my homework because I have to do 10 models, or do I take a day to do it, sort of thing. Okay, other questions? Cool. The other thing we haven't talked about is how to choose NB. NB is the size of your batches. Your batch sizes can go from very small to very large. The larger it is, the less variance you'll have on that estimate of your gradient. And so the more likely you are to go in the right direction, the higher your learning rate can be because you're going in the right direction. Part of controlling your learning rate has a lot to do with the variance of getting a sample that points you in the wrong direction and not moving in the wrong direction a bunch of times. So the higher NB is, the higher your learning rate can be. The lower it is, the faster your iterations are going to be. So each iteration, if you're evaluating 10,000 data points versus one data point to calculate that gradient, with one data point, your gradients are going to be pointing in the wrong direction all the time. So you're going to have to take much smaller steps. But theoretically, you can take 10,000 steps in the time it takes to do one step in this better direction, sort of thing. So selecting your batch size is a little tough. Generally, what you do is, what most people do is they look at their computer. You select your batch size so that it efficiently computes. So like if you're doing this on a GPU, often we will be doing, we'll be working with a highly parallelized sort of thing where it can do 256 examples in the same amount of time as it can do one example. Just because GPUs are built to do this huge amount of parallel processing. So generally, you'll use a batch size that's dependent a lot on your architecture. If you're doing on the CPU, maybe 256 is too much because we can't do vector processing of that size. But if you do size 1 versus size 16, it's almost probably going to be about the same cost with good vectorization code. Just because CPUs do vectorize things, can vectorize things well if you write it correctly. So the sample size is gonna depend a lot on your computer. There's no real good good rule of thumb. For our homeworks, we'll probably just use batches of 1, just because it's easy. We don't have to worry about vectorizing it. We don't have to worry about anything. However, it probably won't be the most efficient, depending on what your computer is and what the data is. But don't worry too much about that for this class. If you go and you start applying this stuff in the real world, almost certainly you will use a batch size, which is some power of 2, up to say 256. That's real common, or 128, because that's how well sort of even CPUs can efficiently chunk stuff up when it's a little bit bigger like that. All right, let's see if we missed anything. Okay, cool. All right, so that's it for SVMs, but I do want to do a demo that I wrote yesterday just to show you guys this. There's an off chance this will work. So what I did was I wrote a little, this is just a Python notebook. And I didn't do an SVM because you guys have to do an SVM for your homework, and I didn't want you guys just to take my code and use it. This is linear regression. So basically, I'm going to be fitting to a line, but the cost function, what we're going to have is basically a bunch of points that are in a line with some randomness, and we want to find that line. So the cost function is, again, going to be some ax plus b. This is going to be where I think the point is on the line. And then y is going to be where the point actually was in my input data. And so I just have a cost function, which is the the square of the difference there. And this is real common. This is just sort of, often you call this least squares. You're just going to find something that reduces this square down to a low value. Again, we do have some regularization parameter here. Did I call this a regularization parameter at any point? Does anybody hear that term before? Okay, that's a little bit of a oversight on terminology. This guy, when we talked about reducing the size of A, sort of constraining the size of A, that's called regularization. And that's important. You're going to hear that term a lot. We almost always have regularization on our learners. And it's just a way of sort of taking a learner that might be very, sensitive to the training data and sort of smoothing it out so it'll generalize better on future data. So this type of regularization is called L2 regularization because it's an L2 measure. Anything squared is an L2 measure. So this is just called L2 regularization. And we will talk about L1 regularization later on. But it's a regularizing term. These are going to be on almost all of our learners, so it's important that you at least have heard that term. But anyways, back to the demo. So we got a cost. Again, in my case, I just did it for a single dimension. You guys will have to do this for inputs that have some d-dimensional input vector. So again, I did that sort of on purpose so that you guys didn't get to use my vector code and just sort of change the formula slightly. So you'll have to do a little more work in order to do this. But we can look at the gradient of the cost with respect to both A and B. They're very similar to the SVMs. They're just slightly different derivatives. The other one, the SVM uses the max with the hinge loss. This is just the least square loss. But then I just wrote those up. Basically, I took this exact thing and I implemented it in a couple functions that return the cost and the gradients. I think I executed all this stuff, but in case I didn't, let me do it again. I then wrote a bunch of animation code that you guys don't need to see because it's horrible and ugly. And then we have the step, and this is just exactly what we talked about. To take a step, you have some current A and B estimate. You have the parameters and the learning rate you're using. And then you basically take the gradient. I'm not sure why I calculated the cost there. You don't actually need to calculate the cost. I never use it, actually. But you take the gradient, and then you adjust the estimate each time using the formula that was in the notes. So pretty straightforward. And then this is just the stochastic gradient descent is just repeating that step over and over and over for a random batch each time. So here I take a random thing, I take a step, and then I do a bunch of stuff so that I can animate it here. So let's just look at that. These run super quick. It's done for my thing. But then the animation code has to actually draw each one of the frames. So that's what's actually running here. So what I had here is I chose an eta of about 0.04. And I drew 3 graphs here. This one on the left is in the parameter space, not the feature space. So this is the A and B parameters. And we're going to show how those A and B parameters move around the space as you take steps. And this little green dot is where we should end up. This is the cost function. I'm not doing classification, so I couldn't do the accuracy. So I couldn't draw a nice graph with all the accuracies. But the cost function will sort of have the same patterns. It'll be really jagged if your learning rate's too high. It'll be super smooth but not really moving if your learning rate's too low. And then it'll be noisy but going sort of down if your learning rate's kind of in the ballpark. And then this last one is actually, these are the data points that I'm trying to fit. And I'm going to show the line that we're actually learning as we go. So I can just run this once so it doesn't jump around. So this is actually the learner. You can see it quickly sort of zooms in from, I started way over there. It quickly takes a couple big steps. It overshoots initially, and then you can see it overshot right up here. And then it came in, and it slowly came down and got to a good point. And again, we had an initial pretty big drop in the cost, and then it kind of kept going down, but with a little noise. That's exactly what we expect. So I'm going to do this one, and I'll have that one start calculating too. This one is if our learning rate is too high. And what we're actually going to see is this learning rate actually diverges because it's fairly high. So the estimate we get is going to be way wrong. So let's click that. So we actually started in the ballpark. But the scale on this guy is much different of the parameter space. So the other parameter space went from basically 0 to 1. And this one goes from, is way bigger, 20 to 25 sort of thing. And it started right in the middle, or right at the beginning there. Oh, how do I reset that? Go back to the beginning. It starts up where it should, but because our learning rate's too high, we're taking too big of steps, we're going too far, we're overshooting the minimas, and we're constantly going back and forth farther and farther away, and it just gets worse and worse. So a learning rate that's too high, sometimes you won't learn, but you'll stay in the ballpark. Sometimes you'll diverge and go all over the place. And as you can see, the cost function here, it started here. It went down initially because we were in the ballpark. We almost got close to it, but then we overshot it, got really bad. It went up and down and up and down and all over the place. And then you can see actually the line over here, it's just bouncing A and B all over the place. So the line is all, sort of all over the place when it's doing it. And then the last one is, this is just too low of a learning rate. And run that once. And this one, what you're going to see is the cost is going down, but it's taking very small steps. There's very little variance in the error, just because, in the cost function, I mean. This guy is very smooth because we're taking very, very, very tiny steps. So if we take very tiny steps, we can't really move the cost too much. And again, this one will just never gets to where it needs to be. You can see it's slowly getting there. And eventually it would have gotten to a good answer. But it took much longer than that first one, which got there fairly quickly. So that's sort of the idea behind learning rates. And again, this will give you a sort of an idea of how we actually translate the equations in the text into code, which is something people really had trouble with for the second homework last time. It's actually not a lot of code, but figuring out how to do that translation can be a little tough. So you at least have some idea now, hopefully, how you do that translation from the gradients into some actual code. Things I didn't do in here, I didn't do lambda estimations. I didn't actually do a hold-aside validation set for the season. I just used the training set itself, which is the full training set, which is actually a bad thing to do generally. It's going to give me an overestimate about how good I'm doing. So this is not your homework. Don't just turn this in. You will probably not get full credit. But it'll give you somewhere to start at least. Any questions on that? Is there a summation in the derivative? There probably should be a summation somewhere. I'm catching myself on that. Let's see. Oh, yeah. In the gradients? Oh, yeah. Where did that go? Probably should correct that. There should be a 1 over n on both of those. Yes, there is definitely a summation over the different y's and i's. Yeah. Oh, I can do that. Yeah, these are the examples. Yeah, sorry, I had done the gradient for just the a single example basically, but yeah, we have to sum over all the examples in a batch. Again, with stochastic gradient descent, we sum over the batch, not over the full data set. Anything else? Cool. Okay, that's SVMs. And now we're going to move into a whole nother topic. And that topic is, this is actually going to be Chapter 5. Chapter 5 is about working with high-dimensional data. And this is going to take a couple classes where we're going to talk about a bunch of techniques to basically first visualize high-dimensional data, to transform it and do different things with it, to kind of get a feel for what's going on in high-dimensional data. A lot of times we're almost always going to work with dimensions of data that we can't visualize. And so we're going to try some techniques to first visualize it, and then often we'll fail, but we'll try to find some ways to still spot, say, mistakes in the data, issues with the data, and to kind of look at the structure. One of the important things to understand about high-dimensional data is that our intuitions about how dimensions work really start to fail at high dimensions. And we're going to see some of that later on, where things you kind of think about and reason about in sort of a spatial way fail at high dimensions. An example of this is that, we'll prove this later, but an example of this is that in a low-dimensional space, if you take a shape, let's say a circle, a sphere in 3D, and you sample points out of the middle of that sphere, almost all of those points are going to come from the interior of the sphere, because there's very little skin on the sphere. If you think of sort of like an orange, and you think of the skin versus the non-skin part, almost all the points are in the middle, in the non-skin part. However, at high dimensions, that's not true. At high dimensions, almost every point, if you were to sample randomly, almost every point is going to fall on the skin of that orange. It's very counterintuitive in the high dimensions. And it's actually easy mathematically to prove this, but it will break our intuition a lot when we start trying to reason about how distances work in a high dimension. It's one of the reasons that nearest neighbor doesn't work in high dimensions. It's because distances, it turns out that points are almost always really far from each other in a really high dimensional space. Even fairly similar points can be fairly far from each other. So let's just start. I'm going to go back to the monitor here and look at the book for a second, just because there's some diagrams in here. Let's start by talking about how to visualize things. So the first most common way to visualize high-dimensional data is projections. So projection just means that you take, say we want to do a 2D projection. We take everything but the two things we're interested in, and we ignore them, we give them a value of 0, and we look at what's left. So in this case, in this example here, this is it's called the petal data set. It's basically a data set where they took 3 species of flowers, related flowers, and then they measured, there's 4 things they measured, I think. It was petal width, petal length, sepal width, and sepal something else. I can't remember what the other one is. It's down below. We'll see it in a second. And so one thing we can do is we can take those 4 dimensions and just ignore them. This is straightforward projection. If we ignore 2 things, we end up with something that looks a little bit like this. you'll notice that there's 3 types of flowers. There's the pluses, the X's, and the little O's there. And all we've done is looked at petal length and sepal length. We've ignored the 2 other things. And what you can see is it's pretty clear that this is divided between the pluses and the group of X's and zeros. But the X's and zeros are kind of mixed up. So we couldn't really distinguish between the X's and the zeros in this case. However, if we look at this in 3 dimensions, and I still think we lost a dimension here. I think we'll see that in a second. You can kind of see that in 3 dimensions, the X's here are probably pretty well separated from the O's up here. So projection always loses information. Well, not always, I guess, but typically it loses information. It can be pretty useful to look at data through a projection, but you got to be careful because it's going to often overlap data, and sometimes it won't really give you a full story. So this is the first thing you often do is you just project your data down, take a look at it. The next thing you do is, or you can do, is you can look at stem plots. Stem plots are just plots of the mean usually for the different classes. The one on the right hand is the interesting thing here. This is a wine data set. There is 13 or maybe 12 different features in there. And so one thing you can do is you can take the means of each of the classes and just plot them on this stem plot. So this is feature 1, feature 2, up to feature 13. And what you see is for a lot of those features, you can't really say much. For this one, you can see that there is some separation based on that feature. So sometimes that's useful. And again, these are the means of the classes for a given feature. It's useful. I rarely see stem plots, though. I don't know that I would have, if I was writing a book, I would have put them in there. I've never actually done a stem plot because often you will just get a kind of a blob of stuff that you really can't tell much. For low-dimensional data, still greater than 2, but less than, say, 10, you can do this sort of setup. This sort of setup is called a panel plot. Panel plots are interesting in that you view basically all the projections, 2D projections at once. So here you can actually see, you can look and try to find projections where things are separable. And so here's our sepal length versus sepal width. And we can see that things are kind of muddled here. But there are other projections where you can actually separate out those classes. So you can kind of get a feel for whether the data is separable or not with these panel plots and kind of get a feel for the layout. Again, it doesn't work for high-dimensional data just because as soon as you get past, say, 7 or 8 of these panel plots, they just start getting really tiny and all mushed together, and you can't really tell what's going on anyways. But for some of the stuff you guys will be doing, panel plots, in R, I will guarantee you there is one single call that will generate this sort of thing. So if you wanted to do a panel plot in R, it's super easy. In Python, it probably exists. I've never actually tried. All right. Then we want to look at, this is a panel plot for, got a little big there. This is a panel plot for another data set, and there's something we want to sort of look at in this particular data set. This is called the height-width data set. It's a bunch of features. I think there's 10 features. We're only showing 4 here, but it's a bunch of basically measurements of people and a bunch of physiological things like their age, their weight, their height, their adiposity, which I don't know what that is, and a bunch of other things. And they're plotted into a panel plot. The important thing to get from this particular thing is that if you look at some of these guys, like this, let's see, height versus age here, you'll notice that it's pretty flat in the height. Now, of course, this could be just an effect of scaling. That could be an issue. But if we go to weight versus adiposity, we also see kind of that effect, ignoring sort of the scaling. It still has sort of this sort of cigar shape where it's that can't just be a scaling issue of one of the axes needs to be expanded or something. It is actually sort of this thin-shaped cigar. And this is a point that's important in high-dimensional data, is that often David, who wrote the course, likes to say that often low-dimensional things hide in high-dimensional space. And so what we see here is there's actually some fairly low-dimensional effect going on where several of these features are very highly correlated. And so whenever you have a high correlation between features, effectively there's a dimension being eliminated there. If you have a correlation of 1 between two different features, one always moves with the exact same way as the other, essentially you've eliminated a dimension from your data. If you can almost always transform these things into a lower dimensional data set. And that's a lot of what we're going to be doing today and in the next couple days, is doing transformations to take these low-dimensional things that are embedded in a high-dimensional space, shift them around so that we can view them in a low-dimensional space. All right, so let's go to that. How are we doing on time? 10 minutes. Okay, so the nomenclature of the book, I'll try to stick to that. It's a little odd, I think, at times, but he used those brackets around an X to indicate that we have a set of data. So basically, this is equal to some set where you have, sort of a X vector 1 up to X vector n. So it's a big set of data. So often if you see brackets, that just means you have multiple examples. And sometimes it's important to be clear about that. So the things that we can start looking at when we start wanting to do analysis, we'll often look at the mean of X. The mean of X is, really obvious. It's just going to be the mean over all the data points. And remember, these are vectors. So when I say the mean of X, it's going to spit out a mean vector, which is the vector of all the means. So you're averaging across all the different data points, and you get the mean for each of the features out in a vector. So obviously, we're going to use the means quite a bit. We're always going to look at those. But going beyond the mean, let's consider really quickly a data set A, which again is just, for now, we're not going to, I'm just interested in A through N, B1 through Bn. And let's just say those are scalars for the moment. Then we can calculate something called the covariance, which hopefully you guys have all heard of. And we'll often write it either AB or, just because I sometimes screw this up, I'll leave the brackets in. Sometimes I'll take them out. I just want to show that in different ways because they mean the same thing. The way that the book is written, you always have the brackets there. Sometimes you drop the parentheses and you just leave the brackets, but I will often write it incorrectly. But these mean basically the same thing. It's the covariance over that set of A and that set of B. And the covariance is I equals 1 to n of ai, oh, I've forgotten how to spell mean of a times bi minus the mean of b. Covariances don't need to be calculated on two objects that have the same, two sets that have the same number of elements. They can be calculated on different sizes, but for our purposes, we don't care because we're not going to be calculating on anything that don't have the different size. Now, covariance, you almost certainly have seen covariance. If you haven't, you've been kind of living under a rock, I think. The covariance is basically, we're talking about, on average, how often does one element, the first item, how often is it above it? When the first thing is above its mean, how often is the second thing above its mean? Or when the first thing is below its mean, how often is the second thing below its mean? So basically, how often do they move together in some linear fashion? So that's kind of what covariance measures. How often do they move together in the same direction? So one problem with covariance is it's sort of unscaled. It can have sort of a random scale based on the variance. So it's pretty standard to talk about correlation. Correlation of AB is just equal to the covariance of AB divided by the variance of A and the variance of B. Sorry, it's the square root of the variance of A and the square root of the variance of B. That just normalizes it out. And this is always going to be in a value of -1 to 1. And so, by the way, variance of A is just equal to the covariance of A with itself. So the correlation just sort of averages it out so you don't have to worry about scale. And now we can talk about sort of what things look like if they have covariance of 1 and covariance of -1. So, sorry, correlation of 1 and correlation of -1. So if you have data points like this, if they move like that, what's the correlation on those? -1, yeah. So as this one increases, this one's decreasing. What is the correlation on that? Just 1. They're moving up together. And then sometimes you'll have, this is a little harder to draw, but what's the correlation on that? Probably 0. I mean, it's probably not 0, but it's probably close to 0. I don't know why I drew it like that. Let's try that. Yeah, those are basically when one is moving, you don't have any information about the other one. So questions on that so far? This is just pretty standard early statistics stuff. Now we're going to start looking at things when we talk about a feature vector instead of just the individual scalars. All of those measurements I put, or all those expressions I put up above, we were just talking about a single number. Now let's talk about the same stuff but in vector form. So we're going to talk about some x1 through some xd And again, this is just a feature vector. It's a column vector of each of our features. Where if that's the form of X, we can calculate the covariant matrix. And we write that as CovMat, just to be clear. And again, we'll be talking about a data set of the X points. And then the formula is, again, just a summation. And it's almost exactly the same as the other one. You take xi minus the mean vector of x, and you take it times xi minus the mean vector of x again, but you transpose, let me make sure I get that right, xi, yeah. You transpose this second one. And if you did this, remember x is, these are both vectors, so it's a vector times a vector transposed. So you're going to get it's going to do a outer product, not an inner product here. It's not going to be a dot product. You're going to get a big, each one of these is going to be a big matrix of d by d. Then you're going to average over all those. And what you're going to end up with is a matrix that sort of has this form, where you're going to have a bunch of elements. Along the diagonal, if, let's just say this is element R, along this diagonal, this will be the variance of XR. So along the diagonal is the variance. And then off diagonal, let's say it's, let's put this one, which is maybe R, and then let's say this is index S. This will be the covariance between feature R and feature S. So obviously, this is a diagonal matrix. So this value and this value will be the same. They're symmetrical across the thing there, across the diagonal. But the covariance matrix is going to tell you basically all of the covariances of all the different features crossed with the other different features. So this is going to be very informative about how all the features move with respect to the other features. And we're going to be able to play a lot of games with the covariance matrix to do some transformations and whatnot that are going to be pretty useful. The next section, I think I'm going to stop there. We got just 2 minutes left. I'm going to stop there because the next section kind of is going to take more than 2 minutes. But if you guys have questions, I'd be happy to answer questions. Are there any questions about anything? Nope. Okay. I will see you guys on Thursday. Try not to get frozen tomorrow. It's supposed to be like 40 below wind chill. But do go outside and throw a cup of water into the air and tell me if it freezes, just in case I forget to do that. Yeah, that's true. That's true. My girlfriend and I were debating whether we should throw boiling water, and she's like, well, that seems like a bad idea.